Okay, good evening, class. We want to discuss temperature and its measurement. Temperature and its measurement. You have written the notes already, and so I expect that you would pick your notes and then you follow me as I explain. In temperature and its measurement, the very first thing we have there is the definition of heat energy. And what is heat energy? It's a form of energy which flows from one point or part of a body to another point or part in a direction determined by the temperature difference. What do we mean? Let's have one metal which is drawn like that, and then from point A to point B. Let's assume that we apply heat somewhere closer to point A. So we have a Bunsen burner that is supplying heat to point A. Let's heat this part of maybe a metal like steel for about 10 minutes and then try to touch the ends of A and then B. Then we'll be able to know if indeed it was as cold as we started heating, or maybe it's now hot that we cannot what? We cannot hold. So when we hit this very point, after let's say 5 to 10 minutes, we should expect the steel to be red hot, and red hot such that when we touch this point A, we are going to be bent by the hotness. Likewise, when we touch also B, we will also be bent by it. What does it mean? You can see that point A is closer to the Bunsen burner, and so when we touch it, we expect that it might be hotter than point B. But the point is that we are hitting even closer to point A. So how come when we touch or hold point B, we still may not be able to hold on for a longer time, and we may be compelled to remove our hands quickly? This is because whenever heat is applied at a point, the heat flows from the point it is applied to all other parts. In other words, we do say that heat will flow from a point of higher temperature to a point of relatively cold or lower temperature. So what do we mean by heat energy? Heat energy is a form of energy which flows from one point of higher temperature to another point of lower temperature. But in what direction? In a direction that is from a higher temperature to a lower temperature, or in a direction we say determined by the temperature difference. We all know that heat is measured in joules because it is a form of energy. So heat is measured in joules. Now, heat energy, we do say, flows from one point to the other point until we have almost the entire body or system having the same temperature. What do we mean by the entire body or system having the same temperature? What we mean by the entire body or system having the same temperature is that they have a unique temperature. We do say that such a body has reached thermal. Such a body has reached thermal equilibrium. So when a body reaches thermal equilibrium, then we do say that it has reached it has the same word temperature. So in continuing, we do say in effect, heat flows from a hotter point to a relatively colder point of the same body or another body, because we can happen to heat. Let's assume that we are heating a substance at point A. We are heating a substance at point A. Then there is a substance at point B. They are of different bodies. But in view of heating substance A, we can have heat being transferred from the entire system or from point A and then carried to point B. Though it might not flow in a way that the heat content of B will be very high. However, because of this substance A which has been heated, the environment is heated and then B is also heated. I hope you understand. Good. We have things that heat energy can do. There are two, and one is that they increase the potential energy of the molecules of a substance. Two, they increase the internal molecular kinetic energy, or simply to say, they increase the kinetic energy of the body. So, whenever we heat a substance, still using the substance AB, the steel AB, we heat it. Two things are expected to happen: increase in internal molecular kinetic energy and increase in potential energy of the molecules. Molecular kinetic energy simply means the kinetic energy of the molecules, and as well as when we say molecular potential energy, it means the potential energy of the molecules. So it brings us to the same thing. Good. Let's try to analyze this. Let's assume that the molecules of a substance are at a point here, as my hand is. When you heat it, you are likely to cause an expansion in the molecules, such that any substance that expands means there has been change in position of the molecules. And when there is a change in position of the molecules, what happens? It means there has been an increase in potential energy. Let's use liquids also as an example, or gases. Whenever we heat substances, we heat liquids, we usually will see the vigorous motion of the molecules moving up and down. What do we experience there? In terms of what we are learning, it means whenever we are able to see vigorously the molecules of the liquid moving up and down, it means the molecules' kinetic energy have also been increased. So these are the two effects of heat on substances. We will come to main effects. These are in terms of the positions and then in terms of their velocities. But we'll come to actual effects of heat energy, and we'll see that we have about 4 or more. Let's come to the sources of heat energy, which you already have learned of. Sources of heat energy, take your mind back to JHS. We saw that firewood, or what we should call, firewood, the ones which we burn, they give heat. But before they give heat, we have to at least light the fire or the wood so that they will give it. All the sources of heat that emanate, that come from plants and animals, are termed as biofuels. So biofuels includes firewood and charcoal. Let us take note of that. Let's move to page 2, or if you are using your notes, then let's continue. Nuclear reactions. In chemistry, we got to know, in physics, we got to know that if we can break the tiniest atom, then there is the possibility of what? Of obtaining energy. And that energy from Einstein, Albert Einstein, says that that energy is capable of doing a whole lot of things, is capable of solving a lot of problems for humans. But unfortunately, we have not been able to use or apply that in most of the atoms that are surrounded around us. Let's focus on this and then discuss what we mean by the nuclear. So, in the atom, should we be able to break into the nucleus of the atom, then we should also expect that high amount of energy in the form of heat will be accompanying what we have done, the breaking of the atomic nucleus. So, nuclear reactions will give us heat energy. Again, we have chemical reactions. Chemical reactions in the lab, the reactions of acids, bases, the reactions of acids and some acids, bases and some bases. All those things, they are accompanied by heat energy. Again, we also have fossil fuels. Fossil fuels refer to the petroleum products which we use. What do we mean? We mean LPG, liquefied petroleum gas. We mean the normal petrol, which we know that when we bring fire so close and we are not careful, we can be burnt along with the petrol, which is diesel inclined. Diesel, petrol, and whatever, they are all forms of fossil fuels. When we break them down, we get the various components of kerosene, petrol, diesel, and they all give sources of heat. We also can think about electricity, isn't it? In our homes, our electrical heaters, our electrical pressing irons, they are all forms of obtaining heat from electricity. Now, friction. Yes, when there is high friction between two surfaces, you discuss that in JHS. That can lead to what? To high heat. And a common example is by using the palms. So if we are able to wrap the palm, we wrap the palm separately. Let's do that for 1 minute, 5 minutes, 10 minutes, and then 15 minutes, and see the sort of heat which you are going to what? You are going to produce in your palm. That is heat energy. Though it is that value, it's a value that is small, it is high. Then we cannot talk about sources of energy and leave out the sun. Yes, indeed, the sun gives us the the main forms of energy on earth. The sun gives us heat energy and then light energy, the two main sources or forms of energy. The heat energy is used by inhabitants and people and animals and living things on earth, and then the light energy is mostly used by animals. You cannot even take it out from living plants because they use light energy for photosynthesis. So these are the sources which we have talked about. Temperature. Temperature. It is simply a measure of how hot or cold a substance is. It has not changed from what we knew. Simply a measure of how hot or cold a substance is. Indeed, some books may describe temperature as the degree of hotness or coldness of a body, which is also acceptable. But I prefer that we use a measure of how hot or cold a substance is. The reason is that when you are checking the temperature of a substance, that substance can be hot or that substance can be cold. What can we talk about? We talk about ice, for instance. Ice, we know, can go to the extent of the negatives, negative 10 degrees Celsius. Negative 10 degrees Celsius. And what does it mean? It means that if ice can go that far and we can measure the temperature of ice, then indeed we are measuring how hot or cold it is. Because this one, it is about how cold the ice is. -10 degrees Celsius. Let's go. Temperature, we know, is measured in degrees Celsius. It's measured in degrees Fahrenheit. It's measured in the Kelvin. And the SI unit, the SI unit is called what? The Kelvin. The Kelvin. So the Kelvin happens to be the SI unit of temperature. Do not forget. Do not say it is degrees Celsius. No. SI unit is the system international unit, the recognized unit in the whole world. It says it is Kelvin, and Kelvin is represented by capital K. Capital K. So if you measure a temperature and then you get, let's say, the temperature to be 400, then you write 400 K. 400 K. So that is it. Now, the study of temperature and its measurement is simply called thermometry. What did I say? Thermometry. The study of temperature and its measurement is called thermometry. Now, indeed, whenever we want to check a body's temperature, we are likely to either have it as cold or have it what? As hot. Let me read this section as you have in your notes under temperature. That is paragraph 3. The temperature of a hotter body decreases faster than the temperature of a cold body. In effect, the colder body increases in temperature until the two bodies possess or attain the same temperature. What do we mean here? Anytime you have a hotter body closer to a colder body, then we must expect that the hotter body will be decreasing in temperature faster. Take notice, faster, decreasing faster. Whereas the colder body will be increasing in what? In temperature. And that cold body will increase in temperature as the hotter body decreases in temperature. And a time will come, both will have the same temperature. Now, when both have the same temperature, what do we term it? We term the two to be in thermal contact. Repeat, thermal contact. So when we have thermal contact, when the two bodies have the same temperature. By this, there is a man who worked on temperature by name Zeroth. Repeat after me, Zeroth. Or simply, others will say Zeroth. That is Zeroth, Zeroth. And he brought it in a law he named after himself called Zeroth law. What is Zeroth law? It says what? It says what? If two bodies, A and B, if there are two bodies, let me illustrate here, A and B, are in thermal equilibrium with a third body, C. So, this A is in thermal equilibrium with C. B is also in thermal equilibrium with C. So, if two bodies, A and B, are in thermal equilibrium with a third body, C, then we can say that the bodies A and B are in thermal equilibrium with each other. This is very simple. I will want to always illustrate such using the ages of 3 people. There are 3 people, and I'm using Kwesi, Kwadwo, and Kwabena. Kwesi may stand in for A, Kwadwo may stand in for B, because after Kwesi we have Kwadwo, and then Kwabena will stand in for C. Let's say that Kwesi's age is the same as Kwabena. Kwesi's age is the same as Kwabena. And Kwadwo's age is the same as Kwabena. So if Kwesi is 17 and his age is the same as Kwabena, which means Kwabena will be 17. And then at the same time, you have Kwadwo's age the same as Kwabena. So if Kwadwo is 17, also Kwesi is 17. What does it mean? It means that then it means the two, Kwesi and Kwadwo, also have the same temperature or the same age. So it is the same thing as Zero is saying that if two bodies A and B are in thermal equilibrium with a third body C, then the two bodies A and B are in thermal equilibrium with each other. Good. So don't forget Zero's law. If two bodies A and B are in thermal equilibrium with a third body C, then the bodies A and B are in thermal equilibrium with each other. Temperature we know is measured with what? With a thermometer. And there are different types of thermometers. In our next lesson, we'll be looking at the types of thermometers and what we use them for. But with where we are, let's just look at the option of we are looking at the option of calculating for temperature. Calculating temperature can be very simple. Very, very simple. Let's assume that our temperatures are to be changed from degrees Celsius, where most of us are common with, to the Kelvin. What would the formula be? So then, the temperature T will be equal to whatever value in degrees Celsius we have, theta, plus 273.15. So what does it mean? It means that our temperature in Kelvin, if we have 0 degrees Celsius, so this implies that 0 degrees Celsius is equal to 273.15 K. So this one, everything K. So assuming we are given by theta is, let's say, 20 degrees Celsius, then our temperature in the Kelvin scale is equal to theta. Where is the theta? 20 degrees Celsius. But here we will not bring a degree Celsius, so 20, because we are adding to get Kelvin, plus 273.15 all into bracket K. And when you add, what did you get? I guess you agree with me that you had what? 293.15. Good, if you had it that way. So T is equal to 73.15 K. And thus you will agree with me that if you have to change this one also from the Kelvin scale into the degrees Celsius, what then do we have to do? We will need to what? To subtract 273.15 from this in order to give us back to what? Degrees Celsius. So let me give you one example and then you try that. So change 421 K into degrees Celsius. Wow, very simple, isn't it? So what will it be? Solving together solution, it's going to be theta, because we use theta for that in degrees Celsius and T for that in Kelvin. So theta is equal to, the value in T will be given by T minus 273.15. Let's do that subtraction. 421, the unit wouldn't come, minus 273.16. And what value are we getting? Use your calculator. And I think that I will get 100 and then 21. Then I am having 0.15. Then I'm having here 73. So 16. So 16 plus 121, that is 137. And then we will have 85. So 137.85 degrees Celsius. If you have that, then you are also correct. All you need to do, know the formula. The formula for that of changing from the Kelvin or the Kelvin scale to the degree Celsius scale is that we are going to subtract 273.15 from T. And then if we are also changing, we are changing from the degree Celsius into what? The Kelvin scale. Then we need to add by 273. Try examples on your own. Quote any value you have. You can quote a value like 98. You can quote also 127 degrees Celsius, and you can change it to the Kelvin. You can also quote a value like 42 Kelvin, and you can change it into degrees Celsius. But if you have 42 Kelvin and you are changing to degrees Celsius, then the question is, would your value be positive or negative? What was your choice? Did you pick negative? If you picked negative, then you are correct. If you picked positive, then it means you need to replay this and then get it clearer. Because when we have it in Kelvin, we will subtract 273.15, and 42 minus 273.15 will give us a negative value in degrees Celsius. I'll pause here, and in our next video, we'll look at how to convert from the Kelvin and Celsius scale to the degree Fahrenheit scale, which is also very simple. And then again, we'll continue to look at what we mean to say fixed points. We'll also look at what we also term by thermometric properties. So go and look out for what thermometric properties are, examples of thermometric properties, and then come. And then when you read through, you understand. When you come, when we meet, it will be easier for us to share ideas. It will be easier for us to communicate. It will be easier for us to understand. Bye bye.